Moving forward from our look at traditional machine learning, we need to address its biggest limitation, the reliance on human-driven feature engineering. The bottleneck here is the human expert. In the traditional workflow, a clinician must explicitly define and measure exactly what the computer should look for before the algorithm can even begin to process the data. Deep learning bypasses this manual step. In a clinical context, these systems are designed to learn hierarchical representations of the data on their own, discovering patterns directly from the raw source. We can see the difference in these two workflows. Traditional machine learning requires manual bounding boxes and predefined variables. Deep learning ingests raw pixel arrays, independently computing which areas contain pathological information. This lets the model deduce complex features, like an ECG's QRS complex or a lung opacity, without a human ever writing rules for those shapes. This shifts the primary challenge. The task is no longer about engineering individual features, but about aligning the correct network architecture with the specific data being analyzed. Deep learning is not a single all-purpose tool. In healthcare, models must be highly specialized. Most clinical data arrives in three distinct modalities: one-dimensional physiological signals, two- and three-dimensional imaging, and unstructured text. For a model to be effective, its architecture must be structurally matched to the spatial, temporal, or semantic shape of that data. Mastering this modality matrix is the foundational step for anyone applying AI to real-world clinical practice. The first modality involves one-dimensional, time-series physiological signals, like the continuous data from an ECG. This data is notoriously difficult to process because it is continuous, noisy, and highly dependent on the order of events. In these sequences, the data point at second SOR is mathematically dependent on what occurred at second 3. To handle these sequences, we use recurrent neural networks, or RNNs, and 1D convolutional neural networks. RNNs are architectures designed specifically to process sequential data by maintaining an internal state or memory of previous inputs. These networks use a moving window to scan the data stream. As the window slides, the model retains a memory of previous points to provide context. This memory function allows the network to classify complex arrhythmias directly from raw voltage without manual measurement. However, this creates a data problem. Hospitals generate millions of hours of ECG data, but it is impossible for humans to label and annotate all of it for training. We use unsupervised learning as a workaround. Unsupervised learning is a method where the model learns from the data itself without needing human labels. By hiding parts of a signal, the model is forced to predict the missing pieces, teaching it the underlying baseline rhythms. These sequence-based networks take raw, noisy voltages and turn them into discrete, actionable clinical events. The second modality covers two- and three-dimensional spatial data. This includes the most common imaging formats: chest X-rays, 3D MRI volumes, and whole-slide histopathology. The standard tool for this modality is the convolutional neural network, or CNN. CNNs are architectures that use mathematical filters to scan an image and identify a hierarchy of spatial features. CNNs process images in overlapping grids. The first layers identify simple edges and lines, which deeper layers mathematically combine into the complex shapes of human anatomy.
This allows models to perform highly precise tasks, like tracing the exact boundaries of a brain tumor. The bottleneck for imaging is data scarcity, as strict privacy laws limit the number of scans available for research. We solve this first through transfer learning. Transfer learning is a technique where a model developed for one task is reused as the starting point for a different task. A massive network pre-trained to recognize millions of everyday objects already understands the basics of shapes and edges. We can take that foundation and fine-tune it on a specialized set of medical scans. The second solution is the Generative Adversarial Network, or GAN. GANs use two competing networks to synthesize entirely new images that are mathematically indistinguishable from real scans. By generating synthetic variations of a lung nodule, GANs allow us to create massive, diverse training sets without ever needing to access new patient records.
CNNs, combined with transfer learning and GANs, allow us to overcome the visual limits of the human eye and the data limits of our institutions. The final modality is the massive volume of unstructured text and medical literature. This includes lab reports, triaging notes, and the vast narratives within electronic health records. To process this, we use transformers, like MedGemma. Transformers are neural network architectures that process sequential data simultaneously, rather than one word at a time, allowing them to understand the broad context of a sentence. The core engine of a transformer is the attention mechanism. The attention mechanism is a process that allows the network to assign different weights of importance to specific words based on their relationship to others. This mechanism weighs the clinical importance of every word relative to others in a patient's file. It can link a symptom on page 1 to a diagnosis on page 50, extracting specific metrics from disorganized reports to automate patient triaging. By identifying these contextual links across thousands of pages, the model turns a disorganized narrative into a structured timeline of clinical events. This transition converts the semantic chaos of a patient history into a digital foundation for computable clinical reasoning. Many clinicians hesitate to use deep learning because they view it as a black box that provides answers without explanation. We can solve this through visual explainability tools like GradCam heat maps. On the right, this thermal heat map highlights the exact pixels that the neural network used to make its decision. These maps prove exactly where the model is looking, ensuring it is focused on the actual tumor and not on irrelevant image noise or bias. Integration in the clinic is becoming a collaborative process. Deep learning is not a replacement for a doctor. It is a tireless, high-speed second reader. This second reader can extract quantitative data from scans and signals much faster and with more consistency than any manual method. The next step for the field is the development of multimodal foundation models. Multimodal foundation models are systems trained on diverse data types simultaneously, allowing them to cross-reference different formats in real time. In this unified system, an ECG waveform, an MRI scan, and a text report all flow into a single network node. The model weighs all three streams at once to produce a singular diagnostic probability score. By translating signals, images, and text into one computable language, deep learning aims to scale the holistic diagnostic expertise of the physician to every patient instantly.